Me when I'm talking about power, what am I talking about in terms from a statistical standpoint?
The ability to not commit a type 1 or type 2 error.
Okay, be careful. Not the type. What's our correction or what's our protection against type 1 error?
The alpha.
The alpha. And so what is power then?
Protection against type 2.
Yeah, not necessarily protection, but sort of our likelihood of committing a type 2 error, right? So power, conceptually, you can think about this as the long-term probability of rejecting the null hypothesis when the null hypothesis is false, right? The long-term probability of detecting an effect that's there to be found, right? And so this often ends up being sort of the far and away the most frequent error we likely make in psychological research because our samples are small and kind of limited, right? And so when we fail to reject the null hypothesis, we're not saying that there's not an effect, we're just saying that we don't have sufficient evidence to claim an effect, right? So we might find differences that are going in the direction that we would expect. It's just the difference is small and sort of doesn't sufficiently exceed the effect, the difference that we might expect just because of just random sampling variation and things along these lines, right? And so a couple of different ways we can go through and think about power. One way, and we finished up with this last time, is this idea of, let's say that we have two different populations, and these populations do have a difference, right? So the mean of population 1 is 9.5, mean of population 2 is 6.5, and this is the standard deviation or estimate of variability of both these populations. So we have similar variability, but different means, right? And so if we were to go through and randomly select 20 observations from this population, and then randomly select 20 observations from the other population, right? And then we go through and we calculate a t-statistic for the difference between those two populations. And then we go through, record this, and then just do this a bunch more times. This is essentially what we're doing in bootstrapping anything, right? If we were to do that and then plot our t-test statistics, right? So Nick, what are we gonna find, say with 10,000 replications, drawing a sample of 20 from this population and 20 from that population? What's gonna happen sort of over the course of these replications? Are we gonna find a significant difference in all of these individual experiments? Not all of them, right? Because what we've got is we've got this distribution of t-statistics, right? And what we're going to find if we go through and we identify in this distribution and mark where our critical value is going to be for an independent sample test with 38 degrees of freedom, we're going to find a critical value of 2.04, right? And if we took that distribution and said, all right, here's 2.04, and we went through and looked at the proportion of scores over 10,000 replications that exceeded 2.04, this right here is going to be our power, okay? 86% of values in sort of this of these hypothetical replications exceeded 2.02. I guess that's actually wrong. It should be 2.042, right? Our power for this analysis with 20 observations, assuming sort of these population parameters, we've got power of 0.86, okay? Now, what's going on, Kate, down in this area? What's happening here?
Instances where so is that when you would fail to reject?
Exactly,
Yeah.
right? And so what error have we made right here? Yeah, these are our type 2 errors, right? This is our type 2 error right here. There's a difference. There's a difference between these populations. There is a real difference, right? But in 15%, 14% of the time, we're missing that, right? There's a population to detect. We just didn't get it, right? And so this is the important thing to think about power. Sometimes people say, well, I'm going to power my study. So Haley et al. Found that sort of this effect, and they had 15 people per group, and so that's what I'm going to do. I'm going to power them. So she found it, and I'm going to have adequate power to find this. Okay, that's obviously not correct. Can someone tell me why that's not correct? What's the problem with that reasoning? Haley found it using 15 people per sample, right? And she found an effect, right? Why can't I just say, oh, well, I'm just going to collect the same number of people that she found, and I'm going to be good to go? Yeah.
Because the person who found it in the first place is probably already overestimating.
Exactly. Perfect. Nice work. Okay. Like, this is the thing. If this is the true, that's terrible. Right here is the actual effect. Here's the actual difference to be found, right? And it's this big, right? But Haley happened to run a study with 15 people each, but she just happened to fall out there, right? And with an effect of this size, 15 people in each sample is good enough to capture that, right? But John tries to replicate and fails, and Nick tries to replicate and fails, and Emilio tries to replicate and fails, Laura tries to replicate and fails. We go on and on and on and on, because on these replications, this is where we're falling, right? We're getting something probably closer to the actual effect. And so you just happen to get lucky and fall way out here. Best case scenario, there really is an effect. Your sample just was a bad estimate of the population effect, and it just happened to be larger. Worst case scenario is that this value is 0, and you just happen to, so everybody's chasing after something that's not really there, right? And so this is one way of thinking about power. The long-term probability of committing or 1 minus the probability of committing a type 2 error, failing to detect a significant effect when there's an effect to be had. So over here, in this case, 86% of the time, we're finding that effect, right? With a group size of 20. But sometimes we're gonna miss it, right? And that's just, we sort of hit a whammy here, right? And we just didn't find it. Problem is if this is where we find it's often tough to that whether or not we're looking for something that's not there, or we just happen to sort of be unlucky and fall on that end of things. Okay? So people understand this in terms of replication stuff? Okay, another way to think about things, and this is actually a little bit more flexible, is thinking about conceptualizing power as overlapping distributions. Okay, so if we say we have 2 distributions here, sampling distribution of the mean when the null hypothesis is true. That means there is nothing going on. Okay, so we have sampling distribution when the mean is true, and then the sampling distribution of the mean when the null hypothesis is false. That means in the special case, our most simple case where we're doing like a 1 sample t-test, where our mean, the population mean, or the mean of the population which we're drawing from isn't equal to the reference value, right? And what we see, if we take a look down here, we see an example of these 2 distributions, right? So the null hypothesis, my null hypothesis for this specific example is that population mean is 80, right? And this clear distribution right here is the distribution of all sample means or test statistics that could be captured, that we would expect to capture, assuming that the mean is equal to 80, okay? But if the null hypothesis isn't true, if the population we're sampling from doesn't have a mean of 80, it has a mean of 86, right? What we have then in reality is a different distribution. Here's our theoretical distribution of our outcome, assuming that the null is true, right? But here's our actual distribution under sort of the reality, which is our population mean is 86, right? But you see there's overlap between these 2, right? And so if we go through and we take a look, and we want to say that heavily shaded here in the tail area of the null, right? So this piece, or excuse me, yeah. So this is our alpha level, right? So this is, if we're looking at this distribution, right? Assuming that the null hypothesis is true, this heavily shaded area right here, this is our willingness to make a type 1 error, right? This is where, assuming like, if in reality, the null, the population mean is 80, a small set of the time, we're gonna get values out here, right? And we're gonna claim that there's an effect when there's actually not one. But this is fine, this is what we're accepted as our margin of type 1 error, right? But if in actual fact, the alternate hypothesis is true, if our population mean really is actually 80, all of this gray shaded area over here, what is this? Evelina? What's up? Yeah, this is our type 2 error, right? Because these are values that we're actually getting under sort of our alternative hypotheses, right? In actual fact, our population mean is 86. But for any given sample, are we always going to get 86 as our actual mean? No. We're going to be here, and sometimes it's going to be a little lower, sometimes it's going to be a little higher. But all of this heavily shaded area, this is all your type 2 error, right? These are realities where I'm going to go through and pull an actual value out of my correct distribution, but it's not going to exceed over here into where my critical region would be, where I would need to be able to reject the null hypothesis. Okay, and then this white area, everything from here over, this is the power of my test. Okay, these are scores that I'm going to get in my alternate distribution that are going to exceed the threshold that I set for my null hypothesis, or for my critical value under the null distribution. Okay, so I've got two different distributions here. I've got my distribution under the null. This is what I would expect. I know that even if the null hypothesis is true, I'm not always going to get a test score of 0. Sometimes it's going to be sort of way on the tail. But here's my cutoff, and I'm saying anything beyond this, this is my acceptable type 1 error, right? 0.05 or 0.025% of the time, I'm going to get something in this tail that's hanging out over here, even when the actual population value is 0. But these are just errors I'm going to make, right? But if we go through and we say that's actually the null distribution actually isn't the correct distribution. In actuality, the population distribution is over here, right? It's not 0, it's some value sort of greater than that. And then I've got a distribution here. Well, here, oftentimes I'm going to pull a value from this true distribution, from the alternate distribution, that still falls within the body of my null distribution. And so what am I going to do here?
You're going to fail to reject.
I'm going to fail to reject the null hypothesis, right? And this is why we say and this happens a lot, right? And if we look at this example, our power, or sort of likelihood of making a type 2 error is a lot greater than our actual probability of detecting this effect when it's here, right? This is going to be a poorly powered study because a lot of this distribution is overlapping with the area of our null distribution where we are going to fail to reject, right? But here, right, this is the value in my alternate distribution that coincides with my sort of critical value in the null distribution. And if I get a value that exceeds beyond that, then here I'm going to reject the null, right? But we can see, depending on how far these, how much overlap there is in these two distributions, that's going to impact sort of how much or how often I'm going to go through and reject the null. Okay, and so again, how do we, in our sampling distributions, how do we start shrinking down the variability of our sampling distributions? Okay, so if this is sampling distribution of our null, and this is sampling distribution of our actual hypothesis, or the actual sort of reality, how can I start to shrink down those how can I start to separate these two distributions out? A couple of different ways. One, I can increase the effect size. As the effect that I'm looking at gets bigger, so do these start to become more and more farther apart, right? What else can I do? And this is something that's actually in my power to create separation.
Increase the sample size.
Increase my sample size. Because if I increase the sample size on here, maybe this is sample size 20, but as I start to increase the sample size, what does this do to the variability of my sampling distribution?
Makes it less.
It makes it less, right? And so these start to shrink up, right? And so that starts to create separation. The proportion of the distributions that are overlapping starts to become less and less, right? And so in this situation, here, if we're holding everything constant, right? Here we have a difference of 4 points in the two distributions. Here, though, we have a different situation. We have a difference in 10 points, right? So again, thinking back to some examples, classic examples that Cohen gave, right? So if this is the difference in height between 12 and 14-year-old women, and this is the difference in height between 14 and 18-year-old women, we're going to see a bigger discrepancy between those two things, right? So these distributions are going to be farther apart. And so here we can see this is the distribution of values we would expect under the null, right? But this is the actual situation that we have in real life, right? This is going to be the region under the null distribution that we're saying is associated with type 1 error, right? Or we're going to say very rarely are we going to say there's an effect when there's not, but this is going to be our critical value. So at this critical value here, what is this going to be, Amanda? This gray shaded area here?
That's going to be failed to reject.
Right? This is going to be my this is going to be my type 2 error.
Right.
Over here, this is all going to be my power, right?
Right.
So which one of these examples do I have more power?
The right hand side.
Yeah, this one right here, right? Now, oftentimes we can't directly impact the power of our test. We can increase the reliability of our measurement and reduce some of that error. Usually what we're doing to increase power is going to go increase sample size, okay? So people see kind of how we can think about power. So replication is one way to think about it. But here, from a mathematical standpoint, think about this in terms of overlapping distributions. People kind of seeing what's going on with this? Okay.
So I have a really fast question.
Yeah.
When you were talking about, like, if Haley got an effect and then all of us try it and nobody's getting the effect, how do you figure out that the power's off?
It's hard, right?
Okay.
This is where meta-analysis comes in,
Okay.
right? Because if all of you have run the study, it's similar to Haley's study, right? What we could do is we could go through and say, all right, you failed to reject the null hypothesis, but what was the effect size that you found? What was the, so we calculated an effect size in your study, in your study, in your study, in your study, and then we would look at the effect size in Haley's study, and probably what we would find is the effect size in all of your studies was systematically smaller than Haley's effect size, right? And so what we can start to do with meta-analyses is we can go through and, we don't care about significance, we just are looking at a measure of effect size. And what we can do is on the aggregate across a number of studies, then start to get a better estimate of where these effect sizes using this method, looking at this question, are tending to fall, right? And what we would probably find is that all of our effect sizes are kind of hanging out here, and Haley's is the outlier, right? Now, why? I don't know, right? Probably just random chance, right? You happen to sort of, something happened, you just happen to sort of collect a sample that had an abnormally large difference between the two. Hopefully it's not Haley p-hacking or falsifying data or putting your finger on the scale or doing weirdness stuff, but it's tough to know, okay? Now the problem is if you fail to reject, and 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 you fail to reject, does the general scientific community typically know about that? No, right? So this is what's called a Feilberg problem, right? And this is a problem with our systematic literature is we publish things that reach statistical significance, and if I don't reach statistical significance, then it doesn't get published. So I could have 1,000 attempted replications that failed and 2 that actually hit. All I knew is the 2 that hit, and so my estimate of effect size is sort of what Haley is, and so every time I'm trying to power a study, I'm like, well, I guess I'm powered for a large effect because that's what you found, when in actual fact, we've got a very small effect that we're actually trying to detect, right? And so this is where, again, with an experimental psychology, this idea of this replication crisis, again, if you understand the very basics of sort of what we're doing, it's not shocking. It's exactly what you would expect to happen given the system that we're working with. Questions on any of this? Yeah.
I just have one about the conceptualization of this.
Uh-huh.
The way I was taught is trying to maximize the study, whatever you're doing, or at the same time decreasing that error, which is usually either better manipulation or more people.
Yeah.
Is that right? Or just trying to maximize?
No,
it?
yeah. That's right. And so for a study, let's say I have a study, and this is relevant for you all sort of developing theses and things like that. I've got a study, but it looks like the effect is small, and I don't have infinite resources to go through and collect all the people in the universe. So what can I do? Well, I can go through and make sure my measurements are clean, right? So I've got really precise measurements. This involves using validated measures that have good psychometric properties, as opposed to, I just asked people on a 1 to 10 scale how they're feeling. I don't know. That's measuring maybe what you're trying to measure, but it's probably picking up a lot of other stuff. It's not super precise or reliable. And so if we increase the quality of our measures, that's one way to help clear out static. Another way to do things is start to choose groups that are different from one another, right? So if I look at, say I'm looking at anger, right? So from our intro psych sample, I go through and collect people and give them an anger score, and then I just create a median split and say this is high level anger and low level anger people, right? It's a terrible way to do things. Don't do it. But if you were to do that, in general, you say, okay, this group is generally scoring higher in anger than this group is generally scoring lower in anger, right? And then I want to look at the difference, right? Well, in actual fact, those two groups probably aren't all that different with one another, right? But what I could do is I could go through and say, here, I'm going to identify a group of people who are in the criminal justice system who have been convicted for anger-related stuff, violence and assaults and things like that, and here's a group of people who are very low scoring, right? I've expanded sort of the difference that I'm going to expect in those by selecting populations. Now there's going to be problems with looking at these type of extreme group types of things, right? Same thing in clinical folks. Say Evelyn is looking to look at differences between sort of on some eating pathology type of thing. So you go through and find people who have eating pathology, but you're only including in your study people who are sort of within the clinical range of this thing, and everybody who's not gets pulled out, right? And then I'm going to compare this against people who are reporting no eating pathology, right? So I've got this clinical group and this group that doesn't have anything, and then I'm going to compare the two, right? What we've just done is we've increased the separation of those two things. Happens in my literature a lot. People say, okay, what I did is I looked at a group of treatment-seeking veterans and compared them with well-adjusted veterans who have never met criteria for any disorder ever in their entire lives, right? I've got a hypernormal group, and I'm comparing it to a super clinical group, and so I'm going to say, look at those two things are different. Well, yeah, they should be different, right? What we can start to do with these extreme group designs is start to run into problems with not having differences or effects that might not represent if we're sort of taking into account the whole continuum of pathology. So, and then the last thing we can do, and we'll talk about this when we get into like some ANCO stuff, is you can start to include covariates, right? Things that start to pull up and vacuum up just random variation, right? And as long as that random variation isn't sort of integral to the things that make the groups, that can be an effective way of going through and reducing that error by controlling for hopefully nuisance variables that aren't directly related to whatever grouping thing that you're involved in. Because the other thing you can do is then you can go through like in our area, if you throw in a BDI into anything, I'm going to control for depression. Well, what you've done is you've got a negative affect measure that's just sucked out all the variability and everything, and you're likely not to find anything at all, right? So you got to be smart with some of this stuff. But again, the idea is trying to like either reduce the variability we would expect from that sample size, or and sort of increase that distance. Does that help? Okay. Other questions about this? Okay. Influences on power, all right? Effect sizes, right? If I have, it's easier to detect large differences than smaller differences. If I'm looking at something that is associated with a large effect size, it's easier for me to not commit a type 2 error when I'm looking for things that are very large versus very small. Problem is, for the types of things we're interested in looking at in psychology, what is the average effect size for the things that we're often interested in looking at? Small effect, right? Sometimes I'll get a theses or sort of some type of thing back, oh, and we're assuming a large effect. You shouldn't, right? Because most of the stuff that we're looking at is pretty subtle and pretty small, right? But in general, and this is where some of that extreme group designs start to come into play, if I can make my groups maximally different, functionally what I'm doing is I'm increasing the effect that I'm looking to detect. But problems in finding artificial stuff and stuff that doesn't actually replicate, things that are sort of misleading with some of those types of designs. My alpha level, if I increase my alpha level, it's going to increase my power, right? If I say my alpha is 0.10 instead of 0.05, the likelihood of me making a type 2 error starts to go down, right? Bad news is we can't do this, right? If you try and publish something back, I set my alpha at 0.2, right? What are they going to tell you? Nope, try again, right? So this is something, at least within our field, is oftentimes fixed. Population variance also impacts things, right? All things held equal, as my population variance increases, variability in my distribution of sample means increases, right? Again, if you think about how we calculate standard error, it's our estimate of our population variability over our sample size. We're holding sample size equal. As my population variance increases, what happens in my standard error? It increases, right? Now the issue is we often can't control our population variance, right? Population variance is what it is. Best thing we can do is try and get a measure that's good and sort of doesn't add additional static and variability above and beyond the thing that we're trying to measure. But in general, John, what do we call the variability of a sampling distribution?
Sampling error?
Standard error, right? Did you say that, or did you say it again?
I said sampling, but yeah, standard error.
Like, just take it back. Excellent, right? This is for the fans at home. I'm providing positive feedback. Yeah, that's right. Median, like standard error. That's correct. Yeah, thinking about your standard error is just the variability of your standard of your sampling distribution, right? And what we can do, though, we can't impact this often. Right? We can't, I mean, we can artificially affect this, but in general, the relation is what the relation is. Alpha level, we don't get to fool around with that. Population variance, as long as we've got good measures, that's going to be what it's going to be. But what we can do is we can change our sample size. Our variable of our distribution of sample means, or variability of our the variability of our distribution of sample statistics is going to decrease as our sample size goes up. We're getting more and more precise, right? So we're going to still have variability in our measurement. It's just the variability we expect from sample to sample is going to start to get much, much less, right? And again, remember, thinking about this in terms of if I'm looking at the average height in samples, across samples of 10 versus average height across samples of 100, where am I going to get less variability across those samples? Which one? Less variability across 100, right? My average height is going to be, they're not going to be identical, but they're going to be probably on average pretty close, right? Versus my sample, my mean of sample height for sample size 10, that could jump around a whole lot, right? So this is where we go through and start to pick up power. And so this ends up primarily being with our power analyses. How many people do I need to have to reasonably detect an effect of a given size at alpha level? This is how we go through and try and influence our power. Okay? Questions about influences on power? All right. So how do we estimate effect size? This gets tricky. If we need to go through, and this is what partially what makes power analyses more hand grenades than sharpshooting, stuff like that, right? We're just trying to get in the general vicinity in terms of where we're at with stuff. And so the thing we need to figure out is we need to estimate an effect size. I've got a study. Kate's got a study that she'll do eventually for her thesis, I suppose. And if she wants to do a power analysis, the first thing she needs to say is, okay, what's the magnitude of this effect that I'm trying to detect? Okay? How are you going to go through and get that? Existing research, right? I'm going to go through, hopefully have a good sense. in the past, in the published literature, as people have gone through and tried to detect this effect, what on average is the average effect that they've been able to test, right? Best case scenario, you're looking at something that's been looked at sort of fairly frequently, right? And you're looking at kind of a variation on that, maybe a moderator of that relationship, maybe an intervening variable factor or something like that. And so you're able to go through and through hopefully some well-done meta-analyses when we say, okay, so for example, in my field, lots of people looked at the relation between PTSD and social support. That's something a lot of people have looked at. There's a lot of studies out there, right? So if that's what I'm interested in, I can go through and pull out a meta-analysis and say, okay, this is about the size of this effect across this literature, right? But sometimes we can't, right? Sometimes there's only a couple of studies, right? Maybe 2 or 3 studies that might be out there that have actually looked at sort of this specific thing, right? And if that's the case, our estimate of effect is much less precise, right? Because maybe it's Haley's study and Haley's throwing everybody off in terms of their estimate of effect. Well, I'm going to power my study based on Haley's study because that's the only thing that I have to go off of. But what can happen is then Haley's study is a gross overestimate of the actual effect size, and so I'm in trouble because if I use that as my estimate of my power analysis, I'm going to grossly underestimate the number of people that I need, right? But your existing research is where you're going to go through and look, and people won't also often report effect sizes. So this is why it's important to always report mean, standard deviations, other statistics, so that even if they don't report a metric of effect, you can go back in there and sort of using the information that's provided, reverse engineer an estimate of effect based on what they've provided. Okay? But sometimes there's nothing to be had. Like you may be doing something that literally no one has asked this specific question or looked at this in this specific way. And so I don't know. I've done my due diligence. I've gone through and looked. There literally is no one who's looked at this specific effect. So one thing we can do is we can say, how big an effect is going to be needed, right? How big of an effect would be a meaningful effect, right? So let's say that I have some intervention that I'm interested, so I'm going to provide training to recent graduates on the GRE, right? And I'm going to market this, right? And in order for me to make this kind of a big deal, I want to say, I need to see that this isn't going to increase GRE performance by at least 40 points, because if it's less than that, then it's not going to be worth the time, effort, and things along those lines. So what I can do is I can go through and I can say, well, if the standard deviation is 100, and this is what I need to get, I need to have an effect size of 40. So what I'm going to do is I'm going to power a study to be reasonably, adequately powered to detect an effect size of 0.4. Okay? And then the idea is if I do that, and if I adequately power my study to detect this effect, and then I don't detect my effect, I don't know. I'm not saying that there's not an effect. I'm just going to conclude possibly that the effect that I'm looking for doesn't hit this mark, and if it doesn't hit this mark, then it doesn't matter if there's an effect there anyway, because it's not worth my time or effort, right? So, and this is a hard thing to do oftentimes for a lot of the basic science research that we've done, right? What's a meaningful effect if I'm looking at the relation between sort of attention and some other cognitive sort of process or something like that? Well, from a theory-based standpoint, even if it's small, that could be meaningful from a theory-based standpoint. So it's hard to say, this is the thing that I would need to do, right? From a clinical standpoint, you could say, well, this is the effect that we see with treatment as usual, right? So I need my study to at least get to that point. So if I can't detect an effect of this magnitude, then it's probably not worth it anyway, right? Particularly for applied areas like marketing and things like that. You can say, this is going to be the cost of this campaign. And I need to see this much of an increase in terms of things. So I don't know what the actual effect of this is, because no one's ever done this before. What I can say is if it doesn't hit this point, then it's not going to be worth it or cost benefit to do it. The cost benefit analysis doesn't work out. So what I'm going to do is I'm going to power my study to detect an effect like this. And if I have adequate power, I'm going to say, well, if we have an effect of this size, I have at least enough people to detect it. And then I can say it. And then if I fail, well, I might just be a swing and a miss, but it could mean that even if effect is there, it's not big enough to be something that's worthwhile for me to continue to pursue and then go forward. Okay? People see kind of this type of approach. All right. Other thing you can do, like we're sort of working through with decreasing desirability on how to approach this whole process here. But sometimes what people will do is they would say, well, I don't know. I'm guessing that this is going to be an effect that's associated with a small, medium, or large effect, right? And so in the best case scenario, let's say, well, I don't know. No one's ever done this. It's not really some sort of threshold that I need to get to in order to make it reasonable. But I know that effects in psychological science are often small, at least the effects that we detect. And so I'm just going to power my study to have for a small effect size. Okay. And at the end of the day, you can think about this as being a conservative approach. What often happens is people will go through and they say, well, I ran my power analyses with that. And they said I needed 500 people in each one of my groups. So what I'm going to do is I'm going to say, well, I'm going to assume a medium effect size, right? Because that reduces the number of people I need. Well, you can do that, but you're only cheating yourself, right? I mean, or a funding agency, if they will let you get by with that, right? Because basically what you're doing is sort of running a study that has maybe at best a coin flip of identifying an effect that's there, right? Or like I'm going to assume a large effect size. Well, if you're going to tell me that you don't know what the effect size is because no one's ever done this before, but you're assuming that you're chasing after a large effect, you better have a pretty good justification or argument for why you expect this to be a large effect, right? And why this isn't just a convenient piece or a convenient approach to sort of getting your sample size within something that's reasonable for you to get within your study. Okay, this only with no other options, right? Again, Howell says I don't know often translates into I haven't thought that far ahead. I say I can't. It means I didn't try, right? This is hard, right? You have to go through, you have to know your literature, you have to sort of understand the methodology, you have to go through, oftentimes by hand, calculate some estimate of a ballpark effect size to try and get a sense for what these are at in order to do this responsibly, okay? Questions about sort of approaches to going about estimating effect sizes for some of these power analyses. And this is going to be very important for anybody who goes into soft money positions or any sort of grant funded types of stuff. If I'm giving out money to run through and do stuff, I need to know you have some reasonable, think about me, if I'm going to give you money to gamble and you say, oh, I'm going to play sort of this game that's got about a 50-50 chance, or I'm going to go put all your money on double zeros, I'm going to go give it to the people who have like at least a coin flip on finding stuff, right? This is your power analysis, is you're telling funding agencies, so there's, assuming that this is going on and this is the effect that we're testing, the methodology that I've put together is at least having a reasonable opportunity to go through and detect what I'm looking to detect. Questions about this? Yeah.
I have 3 questions.
Okay, good.
So this is just Cohen's D.
Mm-hmm.
You're just reverse engineering Cohen's D.
Mm-hmm.
Just straight Cohen's D.
Depends on what type of analysis. Right now we're working on means-based statistics, and so Cohen's D is our means-based statistic. As we start to get into other analyses, so this changes.
Okay.
Yeah.
Second question. As far as just notation,
Mm-hmm.
is S the same as SE? Do you use those interchangeably?
Yeah, sometimes. If I've done that, sort of ask me, and I'll let you know which one. Standard error. Yeah, I mean, yeah, I should be better about
But
that.
S squared is my variance.
S squared is your variance, and S is a standard deviation,
Okay.
right?
And SE is the same as S, essentially?
No.
No.
SC is going to be your standard error, and that's a different thing than your standard deviation, right?
Okay.
So if there's points where this is confusing,
Mhm.
shoot me an email and I'll clarify
Okay.
whether or not I'm talking about standard deviation or standard error.
Okay, because I feel like my notes go back and forth, but I don't know
Yeah.
if it's my.
It's probably not
Minus.
on you. It's probably me not being
That's okay.
consistent with my notation. Yeah.
My last question is, so if you do use this to get grant money,
Mhm.
do you ever have to say, like, the question that I asked before, if their statistic, or if their information is underestimating the power,
Yeah.
then
Well-
wouldn't we all be, and how do you defend that to get funding? Does
Well,
that make sense?
you don't know. Maybe you are, but maybe you aren't. Probably it's, I know, so I estimated the target effect based on this study, that study, which all found effect sizes of in this range. And so this was my estimate of effect that I used in my power analyses based on this effect size, and alpha equals 0.05, achieving this level of power, I need to get a sample of expert group.
Okay.
Okay. And then whether or not people find that to be credible is dependent on how well you've made your arguments and how risk averse they are, maybe, or something like that.
Okay, that makes sense though.
Okay. Other questions about this? Okay. So, one concept we want to be thinking about here is this idea, and when we're running power calculations, is our non-centrality parameter. Okay, so our test statistic T. Okay, so our test statistic T, which is our observed mean minus our mean under our null, divided by our standard deviation over the square root of n. Right? This is, what's this called? Laura? Yeah, this is my standard error right here. All this is my t distribution, right? My t-scores are going to be centered around 0 as long as the null hypothesis is true, okay? As long as there is no difference between scores, or as long as my null hypothesis is correct, then my t-statistic is a nice symmetrical distribution centered around 0, right? But if the null hypothesis is false, right? If the mean that I'm expecting isn't equal, or if the actual population mean isn't equal to the mean under the null, then my test statistic isn't centered around 0 anymore. It's centered around some other variable or some other value, right? Because what we're doing is we're essentially subtracting the wrong population mean, right? So this so our T formula, right? T equals x minus mean over standard error, right? This, as long as this value is subtracting the right population value is 0, as long as this is correct, then this statistic has a nice bell-shaped curve that's centered at 0, right? But if this isn't the population mean, right? If this isn't actually what I'm looking for, if there is a difference between populations, then all of a sudden my t-statistic isn't centered around 0, it's centered around some other point, right? And this other point is going to be your non-centrality parameter, okay? Your non-centrality parameter is going to be the difference between the mean of this distribution and the mean of that distribution, okay? And what we would call this is going to be our non-central t distribution. It's a different score. So if I'm calculating a t-statistic, right? And I'm subtracting from the mean of my sample 80, right? If the actual population mean is 80, then this is what I've got, right? Everything falls nicely around 0. Some of my statistics are going to be positive, some are going to be negative, but they're going to fall right around 0, right? But if my mean isn't 80, if the population mean is 90, right? And I take my mean that's from population 90 and I subtract 80, then my t-statistic is going to be positive, right? Everything's going to shift over. And so we call this shift here, and this point right here is our non-centrality parameter, okay? So the shift from 0 under the null distribution to our actual population distribution is going to be, we refer to this as the non-centrality parameter, and this is an indirect measure of power, or excuse me, indirect measure of effect size, right? So again, if we're looking in terms of our power, our question is how likely are we to find some value in the non-central distribution, this one right here, that's greater than the critical value of t under the null distribution, right? So here, my alternate distribution, and this is actually how things happen in real life, but this distribution isn't centered around 0, it's centered around whatever my non-centrality parameter is. In this example, my non-centrality parameter is 1, right? And so if I'm asking about power, I'm saying, how likely is it that I'm going to find some value under my non-central distribution that's at or exceeds the expected value that's associated with my critical value under the null distribution? Okay? So a big part of our power analyses is figuring out what's this non-central what's this non-central parameter right here. And this is part of what's made power complications or power calculations complicated in the past. But luckily, we've gone through and made some increases in computational power and some tools and things like that that help out with this. Okay? So, if we want to power a single sample t-test, right? What we can do is we can start using, and this is like if we were going to do this from a classic approach. What we would need to do is we would need to calculate a test or an effect size, and use that effect size then to get our non-centrality parameter. Okay, and then what I'm going to do is I'm going to take a look and I'm going to get my power for a certain test based on that non-centrality parameter and my alpha level. Okay, so if you grab your power table, that handout that I gave you here. So what we've got, and so this is our single sample t-test. And so if I calculate my effect size for my single sample t, is I'm going to take my mean of my sample, subtract whatever the value is under the null, and so we get a difference there. Take this over my standard deviation, and this is going to give me my effect size. Okay? Then what I'm going to do is I'm going to calculate my non-centrality parameter directly from my effect size. Non-centrality parameter is going to be d times the square root of my sample size. Okay. So we can see, based on what we had talked about here, our effect size is a direct function of our non-centrality parameter. They're back and forth, right? So the difference between these two distributions, this is reflective of the effect that we're wanting to detect, but we can also think about that effect in terms of a non-centrality parameter. Okay. And so with our single sample test, we do this. And so if we run through an example here. So do people seeking treatment for psychological problems have higher IQs? So we go through and we find, so and this is sort of based on this idea that, smart people are crazy, right? And so, yeah, boy, that person's have a lot of things, but they're just a crazy genius, right? And so people have actually studied this, right? And so we go through and we see and get some people who are seeking treatment, right? We see that they have an average IQ score in my sample of 25. They have an average score of 105, right? For our single sample test, we know that we have a mean of 100 in the population and a standard deviation of 15, right? So what we're going to do is we're going to go through, we're going to calculate our effect size. We take 105 minus 100 over 15. What's that give us? 0.33, okay? So our Cohen's d, our effect size is 0.33, right? So based on the data that we've collected, we're finding that our sample is scoring about a third of a standard deviation above the mean of the normal population, okay? So I take my effect size, and I'm going to say, okay, I'm going to use that to calculate my non-centrality parameter. So I take 0.33, and I multiply that by the square root of 25, and what do I get?
1.6.
What's that? Emilio?
1.6 repeated.
Yeah, 1.66 repeating, something along those lines, okay? All right. And so then what we do is we go to our power table, okay? And what we want to do is we want to say, okay, I'm going to go through and I want to test the power of this this setup to go through and so let's say I'm looking for an effect size of 0.33 and I have a sample of 25, right? What's my power to go through and detect this effect, right? So I go through and I take a look at my what's my non-centrality again? It's 1.66. Okay. If I go 1.66 and I look at my delta or my non-centrality parameter, left hand of the column here, and I find 1.66, it's somewhere in between 1.6 and 1.7, right? and then I move over and say, okay, I'm looking at a 0.05 alpha level. Someone tell me about what my power is for this test. About 0.37, 0.38, somewhere in between there, right? So what I know is that if I'm attempting, if the effect that I'm attempting to detect is an effect of 0.33, right? And I've got 25 people in my single sample t-test, I'm saying my power is about 0.38, right? And so we're saying, assuming the null hypothesis is false, my effect is expected to reach statistical significance 38% of the time, given a sample of 25 and a population effect of 0.33. Kate, am I excited about this power?
No.
Mm-mm. That means even though there's a, let's say that based on our data that people who do struggle with sort of some emotional things they're actually smart. This is actually true, but let's say that was, right? But it's not a big effect. It's about one-third standard deviation, or 3/10 of a standard deviation-ish, right? If I'm attempting to detect this effect with a sample of 25, what percentage of those studies over an infinite number of replications is actually going to define the effect that I'm looking for? What percentage of the studies that I conduct trying to detect an effect of 0.33 with a sample of 25, what percentage of those are going to turn up where I'm able to detect that effect?
Does this have anything to do with the example you gave about Haley's?
No. It's, so look at my power. So what percent? It's not very strong, but very specifically, if this is an accurate estimate of my effect size with a sample of 25, what's my percentage likelihood that I'm going to actually find this effect, even though it's true and really there? Yeah, but specifically, what is it based on my power calculation? Someone help her out? Yeah, 0.38. Like 0.38% of the time, right? So am I never going to detect this? No, I'm not never going to detect it. But there's about a 38% chance that I'm going to detect it, right? If I say, hey, come up to this casino table and you have a 38% chance of winning, are you going to put a lot of money down on that? Probably not, because you're going to lose most of the time, right? Not always, but most of the time you're going to lose, right? And so if we're doing an even money bet, then no, thank you very much. I'll go ahead and avoid that, right? And so depending on what it costs in terms of time, effort, money, things like that, to run an actual evaluation with people and say, we may decide that if this is all the people that I can get, 25 is it, we might decide that this study isn't worth running because I've got about sort of a third of about a 0.38% chance, or a 38% chance of actually detecting this effect, even though this effect is a real thing. Yeah.
Would you be able to backtrack and figure out like what sample size would be needed to get adequate power?
Yep, exactly. No, you're exactly right on the same. So we can go through and just reverse engineer these formulas to go through and say, okay, let's say, and this is generally how we should be doing our power analyses, right? Here we're saying, all right, this is my planned sample, and this is my expected effect size. What's the power of this test? This is kind of the opposite way to go through and do these things, but we've done it because it's just easier to go through and do that. What we actually want to know is what's the sample needed to achieve power of 0.80, assuming that we have an effect size of 0.33. This is just simple algebra. You reverse engineer this, and so my sample size is going to be equal to my non-centrality parameter over my effect size, and we take that squared. Okay, and so if we run this out, we've got our non-centrality parameter 2.8 over 0.33. Anybody have an idea where I got 2.8? Take a look at your power table.
80%.
Yeah, right? So a non-centrality parameter of 2.8 is associated at alpha equal 0.05 with power equal 0.8, right? And power equal 0.8 is kind of our standard for acceptable power, right? So I go through and I say the non-centrality parameter I'm looking for that's associated with adequate power is 0.28. So I take 0.28 divided by my expected effect size, divide those, take the square root of that, and so what am I expecting? How many people do I need in my sample in order to achieve adequate power? What do you think, John?
I'm at 72.
Yeah, about 72. 72 people. So if I'm looking with a single sample t-test, if I'm on a reasonably powered test, and I'm expecting an effect size of about 0.33, I need to get 72 people in my sample in order to achieve adequate power. Okay. People see how we've gone through and run these power calculations from a classic standpoint with our power table here.
So is this kind of what Neil was talking about, how like if we just manipulate? The first thing that popped into my head when you said like how many people would I need to achieve power, I was
Mhm.
like, isn't that kind of cheating? Like if we're looking at if we're looking at treatment efficacy, for example,
Yeah.
wouldn't it work for 25 people as opposed to
Well,
72?
and this starts to become sort of a discussion that gets into a little bit of a philosophical. Do I have more evidence for an effect if I detect it with a very large sample or a very small sample? I don't know. People will make arguments on both sides, right? The very large sample is more precise, but I'm also going to be better at detecting very, very small differences, right? If I detect something with a sample of 25, that probably means I've got a big effect. Now maybe it's just a big effect, or maybe I just grossly overestimated my effect based on something that's gone on. I don't know, right? So this is something that we need to think about. And from a treatment outcome standpoint, we also don't want to confuse statistical significance with practical significance or meaningful significance or effect size. Effect size is a separate thing than statistical significance, right? And so if I run a treatment study, having people play in coloring books and stand on their head in the corner, and I've got 10,000 people in my study, am I going to find my standing on the head in the corner with your coloring books treatment works? Half the time, I guess, in the right direction, right? But that effect size might be so small that it doesn't actually have any practical meaning to it, right? And so this is where we go through. And so again, we had you guys read a paper about when effect size, small effect sizes are meaningful, right? There are situations in this where effect size isn't the end all be all, right? But wanting to understand how all these things work together and sort of use that in a flexible way so that you don't, if this was your thesis, right? And you have 25 people and you're really into this project and this is something that you're really bent on doing, cool. You just need to know that it's a long shot that you're going to find something even if it's there, right? And so wanting you to walk into these situations with eyes wide open and sort of recognizing that, hey, I'm underpowered, and so I might not find anything, but that doesn't actually tell me anything. It just tells me that I probably didn't have enough people to detect this effect that I was looking for. And so is that a useful thing to do or not? I don't know. Sort of depends.
So statistical significance is effect size, or we calculate statistical significance.
I will throw you right out of this class.
Okay.
No, effect size is not statistical significance. Statistical significance is something completely different, right? Statistical significance is driven completely by what, if I wanted to sort of had infinite time and resources.
Samples.
My sample size, right? If I just if I just had a sample of 10 billion for everything, then everything's significant. I don't have to worry about it, right? Effect size is different. Effect size is the magnitude of our effect. Now, effect size, things that are consistent with a large effect are easier to detect with smaller samples than something that's small effect, right? But we're not saying that everything with a big effect is a good thing and everything with a small effect is not a good thing, right? That's a big effect. Is it useful? No, not really, because I can just look it around and tell you that that's the case, right? So, and sometimes we have small effects that are meaningful for practical or theoretical reasons. It's just harder to detect those. We need to be more precise in order to see whether or not those are sort of reliable and sort of magnitude of some of those things, right? And so our effect sizes supplement our statistical tests and our tests of significance by going through and saying, okay, so I found something that's statistically significant. This is the magnitude of my effect. Right? So I could find, let's say I'm looking at for an effect size of 0.33, right? If I have 70 some people, I'm likely to detect that effect. Maybe I detect it at p equals 0.04 or something like that. But if I have 500 people in my sample, I'm going to detect it at p less than 0.001, right? So my p-value got way smaller. That p-value looks a lot more impressive. That's just a direct effect of my sample size. My effect is the same thing it was across all of them, right? Evelyn, do you have a question?
Yeah. So this is something that I ran into in doing the problem set, was that the t-test was not significant,
Mhm.
the effect size was.
Okay,
So
hold
how
on right
did-
there.
Okay.
How do you know your effect size
Well,
was
not that
significant?
it was significant, just that it was large.
Okay, perfect.
So how would you talk about that in a write-up?
Yeah, any ideas? So our statistical test was not statistically reliable. So we failed to reject, the null hypothesis and say, we don't have sufficient evidence based on these data to claim an effect that this group's bigger than that group, right? But if I calculate my effect size, I've got a nice looking effect size there, right? How do we account for that? What does this suggest?
That there's a lot of variability in the two distributions.
Okay, you're exactly right. A lot of variability in my sampling distribution, right? And what is that variability attributable to? My standard error. And what, you're on a roll. And what makes my standard error real big? Small samples, right? And so I can find an effect that's quite large, but if I don't have enough people in my sample to detect it, right, then I'm not going to achieve statistical significance, right? I can have a D of 2, but if I got 3 people in each of my samples, I'm probably not going to be able to claim statistical significance. And why couldn't I claim statistical significance? Because my sample size is too small, right? And so this is where we can go through and why sometimes we can't always have adequately powered studies, right? It's just not going to be possible. And sometimes we can go through and we can test things and we say, wow, boy, this is everything. Everything's kind of lining up in the way that I would expect. And we actually have some evidence of a potentially reasonable effect size in the direction that I was expecting. But at the end of the day, I have a cruddy study just because I didn't have the time, energy, or resources to be able to get a lot of people, right? So, Evelina, what conclusions might you make based on sort of the discrepancy that you've detected?
Maybe with like more people we would find the reliable effect.
Yeah, right. Because if I've gone through and I've detected an effect, assuming that my estimate of the effect size is reasonable, right? Which again, that effect size will work on a distribution as well, right? So who knows, right? But assuming that this is an accurate measure of effect, yeah, technically I'm going to fail to reject the null hypothesis, and sort of based on our rules, I can't claim evidence for a reliable effect. Or should we just, nothing more to see here? We should just shut down and no reason to continue on. This looks like a dead end. What do you think? No, right? Because it looks like there's something to be there. If someone had a reasonable study of a reasonable effect size, if it's a large effect, it wouldn't even be hard, right? You just need a few more people, assuming that effect is good and a reliable or a good estimate, and it remains fairly stable. I wouldn't do that. I'd say, boy, based on the data we collected, we weren't able to claim statistical significance. However, we're going through, based on the data we've collected, it looks like so we've got an effect size that's of reasonable magnitude in the direction that we would expect. So certainly would recommend sort of continuing on, maybe taking another look at this with a larger sample size, because it looks like this is more of an issue of power than not actually having no effect to detect. John, did you have your hand raised?
I was just gonna say, I think, but so with that, like with that example, they say that would probably be like a type 2 error or just you're underpowered.
Yeah.
It seems like there's an effect that you just.
Yeah. I mean, essentially, that's perfect. That's exactly another way to put it. Basically, you're saying, I'm assuming I made a type 2 error here, right? I've got a pretty big effect, but my sample was, I don't know, I'm giving you guys just cases with like 5 people in a group or something like that. That's not a lot, right? And so you're in that situation, your assumption would probably be, well, it looks like Bill made a type 2 error, and so I would incorporate that in my discussion, right? Like, well, I've got small samples here, so I'm going to place more emphasis on my effect sizes than my significance test, because I'm walking into this knowing that I've given you all the time and resources and things that I was able to get. This was the best I could do. But what we can do is we can sort of start to not rely completely on statistical significance and start looking at actual effect sizes. It's probably what we should be sort of more focused on anyway, given that our statistical significance is a straight function of sample size, and if I had more time and energy and effort and resources, we would likely see this go through. So again, thinking about this in terms of so the assessment data that we've collected, so we're looking at different correlations and things like that, and we get a correlation of 0.2. I mean, there was a correlation of 0.2 statistically significant.
It depends.
It depends. It depends on what?
Sample size.
Your sample size, right? If I got 400 people in my sample, absolutely. That's significant p less than 0.001, right? If I've got 50 people in my sample, it's not going to be significant, right? It's the same effect, right? The only thing that's making it different is how many sort of people that I have. Right now, at a small sample size, I've got 50 people, I don't know how stable that correlation is, right? And that's the problem. That's why we can't claim statistical significance, is that on replication, that could jump all over the place with a small sample size, right? But sort of not getting all caught up and putting all your eggs in a p-basket value, or a p-value basket, and saying, hey, boy, we were kind of had a limited resources to go through and look at this. It looks like this might be worth pursuing because our effect sizes are fairly, it's worth taking another look at. This is fantastic. I think you guys are getting a hang of this. This is good. It's hard stuff to wrap your head around. How are you feeling about this? Good? Okay, how about this? Let's take a break, come back in 10, and we'll finish up with this. We're not going to talk about ANOVA stuff today. That's fine. What we're doing with an independent sample test, assuming equal sample size, right, is we're looking at power to detect differences in our sample means. Okay? So our test statistic is going to be mean 1 minus mean 2, or excuse me, our effect size, mean 1 minus mean 2 over standard deviation. That's Cohen's formula for D. What's the concern with this, though? What complicates calculation of just Cohen's basic formula? Which one do I use, right? So we're probably going to use a pooled variance estimate here. But then once I calculate my effect size, again, going to get my noncentrality parameter by multiplying D, this time by the square root of n over 2. Okay? Where n is the number of cases in either sample. Okay? Circle this. It's the number of cases in your cell, not all of the people in your sample. Okay? And so again, we're assuming equal samples on this independent sample test. Okay? So let's say that we have 2 treatments or 2 experimental manipulations, and we want to know what the so we go through and calculate my power to detect the difference in means for treatment 1 and treatment 2. So I have my mean of treatment 1 minus mean of treatment 2 is going to be 0.5, or excuse me, 5. I'm going to have a standard deviation, a pooled standard deviation of 10 in this situation, and sample size 25 and 25. Okay? So, my effect size is going to be 5. My difference in my means divided by my pooled standard deviation is going to be 10. Gives me an effect size of what?
Oh,
I mean,
0.5.
0.5. There you go. I was like, oh no.
I was going down one.
Gotcha.
Sorry.
Okay. So we've got an effect size of 0.5, right? So we've got half a standard deviation difference between my two treatment means, right? And so then to get my non-centrality parameter, take 0.5, multiply it by the size of my cells, which is 25, not 50, 25, divided by 2, gives me a non-centrality parameter of what?
One point seven
1.77, okay? And so then I go through and take my non-centrality parameter, 1.77. So what is the power of my tests here? What do you think, Kate?
about 40 or 0.4.
Yeah, 0.4, it's a little bit above that, right? Closer, maybe like 0.43, right? So I'm going to say sort of, and this is the difficulty with these power tables, right? You kind of have to extrapolate between these two, right? But if we go through and we find a non-centrality parameter of somewhere between 0.7 and 1.7 and 1.8, and we look under the column of alpha equals 0.05, we get power for this test at about 0.43. So, assuming the null hypothesis is false, effect is expected to reach statistical significance 43% of the time, given 25 people per group in a population effect of 0.5. Okay. You got a population effect of 0.5, that's a solid medium effect, right? But even with 25 people per sample, which is starting to get at sort of what we would call a large sample, we're still less than a coin flip whether or not we're going to detect this, right? So if this is my plan, right, if I expect to identify a medium effect with my independent sample t-test, and I'm going to have 25 people in each sample, should I be excited about this moving forward? No, right? Because I've only got about a 43% chance of actually detecting this effect, right? The effect is real, it's there, it's at a difference of 5 points associated with a medium effect, but I still don't have enough people in this sample to go through and have it be adequately powered. I'm going to lose more often than I win on this. Okay. Again, if we reverse engineer this, we can detect the sample size per cell. Okay, remember that this is per cell. To achieve power equals 0.08 or 0.80. So again, we're going to take our necessary sample, our per cell sample is going to be equal to 2 times our non-centrality parameter over D. We're going to square that. Okay. So in this example, we're going to take 2 times 2.8 over 0.5. Evelina, where did I get 2.8?
What's the D? This
Yeah.
is
It's my non-centrality parameter, right? So for adequate power, is this ever going to change? Nope, that's always going to be the same value that just goes in there. 2.8 over 0.5 squared, right? And what do I get? How many people per cell do I need to have this be an adequately powered test? Assuming I'm hunting for a medium effect of 0.5. What do you think, Nick?
63.
63. I need 63 people per cell in order to adequately power this.
Why is it times 2? Because it's independent?
Well, because, yeah, functionally, because it's an independent sample. So we've got air from 2 different areas, right? I mean, this is just taking this equation and solving for n instead of, right? So this is just a reformulation of this, right? That's all that is, right? But yes, the reason it's 2 versus independent or the single sample t is because we've got two samples in there. Okay. So how many people total do we need for this study then? 126, right? 63 per cell, 126, right? So in order to adequately power this, we need to more than double our samples that we've planned with this. You have a question here?
Yeah.
Yeah.
So in calculating power, do you want us to just kind of estimate our best guess, or is there sort of a website like the GraphPad that we can use to get it?
Yeah, we'll get to that in a moment. So this is just calculating things by hand using your power table. I want you, because 3 people know how G-power is giving them values, and then you just take as gospel anything that it spits out, which is problematic. So just want to get you a sense for how some of this stuff is calculated. All right. But sometimes we don't have equal samples, and sometimes we know we're not going to have equal samples. Sometimes we know, well, I'm looking at, to get a sample of people high on psychopathy, and I know that's going to be a small collection of folks in there versus normals, and I'm going to have however many I want to have over there. So I'm anticipating unequal samples with this, right? And so what we need to do with unequal samples, we're going to calculate the harmonic mean of our sample size to make an adjustment here, okay? So, and to get our harmonic mean of our sample size, this is going to be 2 times sample 1 times sample 2 over sample 1 plus sample 2. Okay. So, we've got an example where we're wanting to detect sort of power or achieve power for a stereotype threat study, okay? In our control group, we have a mean of 9.6, sample of 18. In our threat group, a mean of 6.58, sample size of 12. Okay? One of my experimental folks, want to tell us what stereotype threat is? Anybody who studies this is aware of what it is?
Just when you feel threatened by some important stereotype, you're going to do worse on something that they're supposed to be better at.
Exactly, right? So if we identify this as a math class, right, and I say there's stereotypes about gender differences in mathematical abilities, we would say that there being men in this classroom is activating gender math stereotypes and then causing sort of downward performance among sort of women in the class. So I always have you do midterm exams in separate gender-specific rooms. It's always not really. I thought that was fun. So, but this idea that we see reductions in performance based on stereotype threat. So in this case, non-specific, we've got a control group here, threat group here, pooled standard deviation here, right? And so what we would do is we calculate our effect size, right? So we've got the difference in our means over our pooled standard deviation, okay? Which gives me an effect size of what? 0.99, okay? And then I take, based on my sample I got, sort of, this is the square root of my harmonic mean. Right now I go through and I have differences in means here, sample sizes. So I take 2 times 18 times 12 over 18 plus 12 gives me, what's the harmonic mean of my sample size? 14.4, right? So we take my effect size, multiply that by the square root of my harmonic mean of my sample size over 2, and what does that give me in terms of my non-centrality parameter? 2.66, repeating, right? And so if I go through and I find 2.66, Kate, what is the power of my test here?
About
0.75, right? So somewhere in there, right? So this is a much better test, right? So we don't have a lot of people, right? But our power is much better, right? So Nick, why is my power much better for this test than some of the previous examples where we had more people?
You're closer to that standard of 0.8, but your percentage of finding statistical significance is much higher.
It's much higher, right? So my power is higher. Why do I have better power in this example relative to some of the other ones? To the last example, for example. Yeah, John?
Looks like you're trying to find a bigger effect.
Yeah, my effect is about 1, right? So so the effect that I'm searching for is exceeding sort of our threshold for a large effect. And so that's why I've got much better power. We're still not adequately powered if our criterion is 0.8, but we're much closer than we were before. Well, we're also looking at a much larger effect. Okay? So notice here though that my effective sample size is 28.8, right? If I take 14.4, which is the harmonic mean of my sample, right? So if I take this 14.4 and multiply it by 2, my effective sample size is 28.8, right? How many people did I actually collect? 30, right? what is this telling me about, what's the impact of unbalanced designs on my power?
You can overdo it.
And not, so so my effective sample size is 28.8. I actually collected 30 people, right? Would I expect higher power with 28.8 people or 30 people? 30 people. So what effect does having unbalanced designs have on the power of your tests? It drives it down, right? So to the greatest extent that you can have equal sample sizes, this helps your power at least on the margins, right? And this starts to become important if I have, like, oh, well, I'm just going to run a test where I've got 10 people in this group and 50 in the other group. Fine, you can do that, right? And I wouldn't suggest removing anybody because that's going to make your power even worse. But in that case, if I've got 10 people here and 50 people over here, I've got a total sample size of 60, but I'm not actually working with power of sample size equals 60. I'm working with something quite a bit less because my harmonic mean of my sample size is going to be much less than what I've got sort of going on here, right? So this is just one of the reasons from a design perspective to think and keep in mind, to the greatest extent I can get those cell sizes reasonably close to one another, the better off I'm going to be, right? I'm not saying you should throw out anybody, that's a bad thing, but you're just not going to have as much power with an unbalanced design as you do have a power as a balanced design. Okay, questions about this? All right. Last thing is going to be our power for our paired sample tests. Okay. Now remember that I had given you a formula for an effect size that I told you never to calculate and report as your sort of effect size for interpreted power, right? That's because that effect size goes into the calculation of power of your statistical test. So what we've got is we're going to calculate for our paired sample test a special metric of effect that we use specifically for the calculation of power. Okay? So what we've got is we've got an effect size here. We're going to take the mean of time 1 minus the mean of time 2. This is sort of the average, the mean of my difference scores here, right? Over sort of an adjusted standardizer. And my adjusted standardizer here is going to be my standard deviation estimate times 2 times 1 minus rho, okay? And rho is just going to be, rho is your population, your Greek symbol for population correlation, okay? So functionally, you can think about this as an R value, where rho is the correlation of time 1 and time 2. Okay? And so remember, this is the sort of the D-paired formula I gave you and said, hey, be aware of this, but don't ever use this or report this as an interpretable effect size. That's because this goes into the calculation of your power. Okay? So again, take a stereotype threat, and let's say instead of a different scenario. Okay, so in the last one, what we did is we had two groups. We had one group performing under stereotype threat, another group performing under no threat, right? And so we went through and calculated power for that assessment. But one of the things we do is we say, oh, well, I thought I heard or remember something that repeated measures are more powerful tests. So maybe instead of going through and having sort of a threat and a no threat group, maybe I just run this as a within subjects design and have people come under threat in one time and no threat in the other, and just run a paired test to see if that makes a difference, right? So my mean at time 1, and let's say we counterbalance this, right? So some people are in the threat condition first and some people in the threat condition second, sort of reordering this. But my mean at time 1 is 9.64, mean at time 2, 7.55, and I've got 30 people total, right? So I don't have to worry about different groups. I can't have an unbalanced design. I've just got 30 people in this, right? My pooled standard deviation across time points is 3.1, and then my test retest is 0.92. So we got a strong correlation between scores at time 1 and time 2. And so what I'm going to do here is I'm going to calculate my modified standardizer. I'm going to take my pooled standard deviation estimate, right? So this is, and by pooled, I'm talking about the square root of the average variance, right? I mean, we can run it through the pooled formula, but if you don't want to, I mean, it's the same number of people, so you can just take the variances and multiply or take the variances and average those and then take the square root of that. That's going to give you sort of this value here. So I'm gonna take my variance at my average variance, square root of my average variance estimate, my standard deviation here, and I'm gonna multiply this by the square root of 2 times 1 minus the correlation between my two values. Okay? And if I do that, what do I get? What is it? 1.24, right? So then I go through and I take my mean at time 1 minus the mean at time 2. This is just going to be equal to the mean of my different scores. I'm going to divide it by 1.24. And what do I get in terms of effect size? 1.69. Okay. And now what I'm going to do is I'm going to just take my effect size and multiply it by the square root of my standard deviation. Now, I didn't have this up there, but where did I get this from? Where did we see this formula for delta? What is it? Not my independent sample, that was, what's that?
Single sample.
My single sample, yeah. And why does this work, Laura? Remember that we can think about
This is
our,
one sample.
yeah,
It's just
exactly.
twice.
We can think about our paired sample t-test, right? As it's just a single sample t on what? The mean of the difference scores, right? If the mean of the difference scores is equal to 0, then that's our rejection, our null hypothesis, right? So remember that our paired sample test is just a single sample t-test using the mean of the difference scores as my outcome, right? So calculating power for the formula I would use to calculate power for my paired sample test to get my non-centrality parameter, it's just the same thing I would use for my single sample test. It's just that I'm changing the calculation of my effect size. Okay. So, and if we do this, we go through. And so what's my non-centrality parameter that I get out of this paired sample test? 9.25, it's massive, right? And so there's not even a non-centrality parameter on the page that goes to that point. So I've got somewhere in I functionally have perfect power with this. I'm always going to find a statistically significant effect in this case, right? So assuming the null hypothesis is false, effect is expected to reach significance over 99% of the time, given a sample size of 30, correlation between my two assessments plus 0.92, and population effect, D equals 1.69. What's going on with the power of this? Okay, I ran the same test as I did with my between samples test, and I was slightly underpowered here, and here I've got infinite power. Someone tell me what's going on. What changed?
The same people at 2 different times.
It is the same people at 2 different times, right? And so that's helping sort of section things out. From a computational standpoint, what changed? What was different across these two?
They're more likely to be similar.
Yeah. But from a numbers-based standpoint, what happened? What if let's say that instead of being an independent sample or a paired sample test, let's say this was independent samples, right? So Nick, if I've got mean in my sample 1 of 9.64, mean in sample 2 is 7.55, pooled standard deviation of 3.1, what's my effect size in a between subjects design? Calculate. So someone calculate an effect size as if this were a between subjects design. Yeah, so if this was a between subjects design where group 1 had a mean of 9.64, group 2 had a mean of 7.55, and the pooled standard deviation across groups was 3.1. So calculate an effect size based on what is it? 0.67. Okay, I thought it was.
I think they said it wrong.
Okay, 0.67. All right. So if we had run this as an independent sample test, right, my effect size would be 0.67. what's my effect size I'm working with here? 1.69, right? Same numbers, right? What made this estimate of effect size so much larger? I made an adjustment, right, for calculating for the correlation between
Your
measures.
denominator's smaller.
Yeah, my
Like by
denominator is
half.
a lot smaller,
Yeah.
right? So what I did is I went through and made an adjustment on my variability estimate here by going through and multiplying by 2, square root of 2 times 1 minus the correlation, right? And so because this correlation was quite large, what is 1 minus that large correlation? Very, very small number, right? And then if I take the square root of a very, very small number, I get an even smaller number, right? And then I multiply that by my variance estimate, and now all of a sudden, because I'm taking into account the correlation between my two measures, that jumps up this estimate of effect much larger than it would be if we were working with an independent sample test, where we're assuming the correlation between people's scores are going to be 0 because they're different people, right? And so what ends up happening is because we're capitalizing on this correlation, we get in our paired sample test a much, much larger effect size, or a much, much larger or more powerful test than if we were to run this in an independent samples test, right? And so again, you can see why I'm telling you never use this formula as an estimate of effect size, because you're going to say you've got an effect size of about 1.7 when you're calculating it as we would a normal effect size. You've got 0.67 versus something that's over a point higher on this, right? But this is important because our paired sample tests are so much more powerful. We need to have some adjustment to go through and account for the power of that test, okay? And so again, our repeated measures design is incredibly powerful, because what we're going to do is we're going to suction off all individual, independent, or sort of individual differences types of things, and we're going to start to calculate, sort of make an adjustment for the correlations between effect, right? So again, we're assuming that we have less noise in our repeated measures designs, because we're accounting for all that individual difference variability, because we're going to partial that out. All of the between subject stuff, we're going to take that out, and all that we're seeing is all we're accounting for is variability in the difference scores. Basically what we're doing is we're carving out noise. So immediately you're talking about like controlling for things and trying to reduce noise. That's functionally what a repeated measures design is doing. All the individual differences across how all of you might approach some, say, measure or something like that, we're pulling that out, and all we're looking at is systematic differences in change from time 1 to time 2. Okay? And so what happens is this correction, sort of the power that we get above and beyond an independent sample test relative to a repeated measures test, is a function of your correlation between your measures. Okay? As our effect size and our power increases, or excuse me, our effect sizes that we use in the computation for power for repeated measures increases as a function of a rho or the population correlation. Okay? So let's say I've got my stereotype threat example, and I'm using a repeated measures design. Am I going to have a more powerful test assuming correlation of 0.5 between time 1 and time 2 scores, or a correlation of 0.8 between time 1 and time 2 scores? What's going to give me a more powerful test? 0.8, right? Because if I've got a really strong correlation between these two time points, if you tell me what you got at time 1 and I know what that correlation, I've got a pretty good understanding of where you're going to be at time 2, right? But as the correlation between our repeated measures starts to approach 0, the power of our paired sample test starts to approximate what we would get with an independent sample test, right? So if my scores at time 1 are completely orthogonal to my scores at time 2, then I might as well just run an independent sample test because it doesn't make a difference, right? But because we've got same people measured over repeated time points, this is rarely the case. Okay. Questions about this? So say I want to plan the power of a test, and I want to figure out, what's going to be on this measure, so what are people likely, what's the correlation of people likely to be across repeated assessments? What should I be looking for in the literature in order to sort of fill this in for my power estimates?
Can you repeat that?
Yeah, so I want to know, in order to calculate power for this, if it's a study that I haven't done, I'm planning for another test, I need to know how closely my measures are going to be in terms of correlation at time 1 and time 2. What should I be looking for in the literature to be able to get a kind of a bead on that? About our test-retest reliability, right? If I give this measure to people at time 1, and I give it measure to people at time 2, and that time point is probably going to be longer than what you expect it to be, right? But if I say a 1 week test-retest reliability is 0.8, if I sort of have you complete this measure twice within the span of like 30 minutes or something like that, I'm going to expect it. So that 0.8 is probably going to be a very conservative estimate relative to what it's going to be across things, right? So wanting to think about where we go to find some of the components for these analyses. Questions about this? Okay, so this is my strong recommendation to you all. As you plan theses, as you plan dissertations, as you plan other projects, any situation where you can incorporate a repeated measure design, it's going to be in your interest to do so. It's going to make for a much, much more powerful test. Sometimes you're not going to be able to, but if you can incorporate this or sort of think about a way, can I run this with the same group of people across multiple assessments? If you can do that, do that. It reduces the complexity, reduces the number of people that you need to have in your design, and it's going to give you a much, much more powerful test. Okay. Questions?
Are there situations, like in more applied, like for me,
Mm-hmm.
that you would do repeated measure?
Mm-hmm.
Okay.
I mean,
Like the clinical stuff obviously pops out in my mind for
sure.
your
If someone,
examples.
let's say that like, I'm looking at sort of a marketing campaign or something like this, and this is my revenue for sort of the past X years, so I kind of know what that is, right? And then so the same company, I go through and have them sort of work in sort of a new marketing campaign, or a number of companies work in a new marketing campaign, and so then follow it along those lines. You're basically taking where people were, companies were at baseline, and now where they are sort of after you've implemented whatever change, that's going to be repeated measure design.
Okay.
All right, calculations with G-power. This is basically going through and just entering values at certain sort of areas into G-power. I have online sort of a screencast video that walks you through power calculations for single sample, independent sample, paired sample in G-power. So I'll give you a link, just go through, take a look at that. It's just walking you through where to go through and enter particular values and sort of calculations and things like that based on these examples. So I'll let you guys go through and take a look at that. The one thing, something went wrong with the microphone, and there's startle blasts that go on intermittently in the video. So just don't make sure that you have it cranked up to the max in your headphones, because that will be uncomfortable. I need to go through and re-record something that doesn't have random static pop into that. But this will do a nice job of walking you through exactly how to go through and calculate these things. It's easy, straightforward. You just need to make sure that you got the right things filled out in the program and everything's turning out okay.
What is G-Power?
What's that?
What is G-Power?
G-Power is our free online program that will be available to anybody who's not using a Mac.
It's
No,
available.
it is on a Mac? Okay, no, is it the Noncentrality thing that's not available on Mac? But okay, so everybody, it's available to everybody, but basically automates calculation of power analyses and things like that. So we're not just using sort of the limited values that are put down on our table here.
Okay.
Okay, and so, Kate, were you the one to ask about like sort of in between or extrapolate? Someone was asking me about that.
Was it me?
Okay, yeah. Yeah, G-Power will do that. So you go through, as long as you know your alpha level, your effect size, and your what power you're wanting to go through and do, different ways you can go through and calculate that, and I'll work through that, and you'll work through that in the video. Okay. All right, so power write-up. How you might go through and put this all together. We might say effect size D equals 0.45, what is expected based on existing data from Jones and colleagues, right? So you're identifying where you've gotten your study. So this is the study that I'm basing my estimate of effect on. power analyses using these data indicate a sample of 32 individuals per group would be required to achieve power, adequate power alpha equals 0.05. 1 minus b, right? Beta is your probability of type 2 error, so 1 minus that is going to be your power equals 0.08. So pretty quick, pretty easy. If you had to sort of, if it was harder to go through and find your estimate of effect size, right, you might have to sort of add some additional details in here. But this is just an example of how you might sort of go through and tie this together. Okay. People know who He-Man is? Show of hands, who knows who He-Man is? Okay, so ish. Last semester, like no one did, and they're like, why? What do you have a picture of a scantily clad sort of muscle dude sort of in there? It's a He-Man. They got themselves educated. So, and then
They remade it.
What's that?
They remade it.
What's that? Did
Yeah.
recently?
I mean, it was a cartoon guy in real life, so it was He-Man in actual life. It's not good. They canceled it. It's bad.
Yeah, with Dolph Lundgren? Because Dolph Lundgren was He-Man in the movie one time. That was bad.
I don't know.
No. I'll look into it. We'll see. Yeah. He-Man is less cool now. When I go back to it, it was very entertaining as a child. I was very excited about the whole thing. I had friends at college who got like the whole thing, just got stoned and watched it. Apparently, that's better that way if you're an adult. But life lessons learned in He-Man. So, all right. So thinking about conceptually, what happens when we fail to reject the null hypothesis when we have an adequately powered study? Because this is going to happen, right? I go through, I do my due diligence, I run a power analysis, but I still fail to reject, right? Couple of different options. One, I made an error in my power calculations. Either I didn't do it correctly, or sort of I had maybe sort of an effect size that was smaller than what's been out there, right? And this is the risk that we run on basing our effect sizes based on the published literature, right? Because we know that there's going to be systematic inflation of our effect sizes in the published literature because we only publish things that are statistically significant, and things that are higher, greater effect sizes are going to be more likely to be published. We're more likely to find effects, even if that effect size just happens to be on the far end of the tail that's not reasonable, right? So I've made an error somewhere, so the effect that I'm actually hunting is smaller than what I had expected it to be, or I'm just a victim of a type 2 error, right? And that's just going to happen. If my power is 0.8, how often am I going to run into a type 2 error? 20% of the time, right? That's still a reasonable. It's not an unlikely occurrence, right? And so the concern is I don't know which one of these is the case, okay? But I mean, if I had to guess, it's probably going to be this, right? And so this is where it starts to become important when we start being realistic about calculation of our power analysis and thinking about sort of what do I use as a point estimate, right? If I use larger point estimates of effect, it's going to be nice because the number that comes out in the sample I need is going to be more pleasing to me. But the risk I run is then sort of getting very excited about something that's I perceive to be a sure thing, and then missing out because actually the effect that I'm looking at is something much smaller. Okay? Again, Wilkinson talking about power analyses most meaningful when they're done before the data are collected and examined. Okay, and so wanting to go through, make sure that we're getting good estimates of our effect sizes and going in and giving ourselves an honest appraisal of the likelihood of obtaining a significant effect based on the sample that we've got. What we don't want to be doing is saying, oh, I can get 50 people in this sample and then sort of trying to reverse engineer my power analysis so that it gives me something that tells me that that's the right answer there. Okay. This is a hard thing. A lot of fuzz going on in this, and so want to just be aware of not tricking yourself into sort of thinking that you're going to find an effect when you actually have a very small opportunity or likelihood of finding it. Yeah. And so, as Wilkinson's saying, sort of the best case scenario, you plan a thesis, and you say, all right, I need to know how many people do I need to adequately power this, and you go through and you run your analyses, right? That's the best way to go through and do this. Sometimes, though, we see people talking about observed power, okay? And we got problems with observed power because what ends up happening is people will collect the data, run their study, and they find that they fail to reject the null hypotheses, right? So we didn't find the effect that I wanted to. And so what people will sometimes do is then, well, let's see if my study was adequately powered. So I go through and I run my power analyses based on the effect size that I observed. And I run my power analyses, and what do I find? If I fail to reject the null hypotheses. Yeah, that I'm underpowered, right? The idea is that what people will try and do is say, okay, I've gone through and I've run my analyses and I fail to reject the null hypothesis, right? So what I want to do now is maybe I go run a power analysis, because if I run my power analyses based on the data that I've observed, and I find that my study was actually really highly powered, and I still fail to reject, then what that means is that the null hypothesis is actually true. Because I have an adequately powered study. If I had an adequately powered study and I didn't find evidence for, and I failed to reject, then that must mean that the null hypothesis is true. Okay? The problem is that observed power is a direct function of our p-value. Okay? There is never going to be a case where you run an analysis, fail to reject the null hypothesis, and then take the effect size that you observed within your study, and then run it through a power analysis, and you find that you had an adequately powered study. Because your p-value and your observed power are directly related to one another. So every time I run an observed power on a non-significant effect, I'm always going to find that I am underpowered, right? And so what ends up happening is we run into a circular logic. Observed power has nothing to add to your conclusions, right? Because if you fail to reject the null hypothesis, I already know that you had an underpowered study. Now that's because, I don't know, maybe because this is my, this is the sort of distribution of my effect sizes that I could get, and I'm right here, so the mean is d equals 0.5, but I caught something that was d equals 0.2, just because I happened to catch it, right? So I just got unlucky. Haley got lucky, I got unlucky, right? But now when I go through and I say, okay, well based on the data that I got, I actually had 0.2 power with n equals 45 per group, right? And if I fail to reject, given my effect size here, am I going to find that, oh yeah, I actually did have adequate power to detect this? No, you're never going to do that, right? And so Honig and Heisey talk about sort of this power approach paradox, where people want to go through, and after they've gone through, collected their data, then say, okay, based on the data that I've observed, and I'm going to calculate my power. I found that my powers, I actually didn't have significant adequate power in this study. Well, we already knew that because you failed to reject the null hypothesis, right? And so we assess, we can go through, and there's certain analyses we can actually calculate observed power, which you can do it if you want, but it's not doing anything for you because it's by definition going to give you, tell you that you're underpowered. Now the rub is, I don't know if I'm underpowered because this is actually the effect size that's, this is actually sort of closer to the population effect size than what I had anticipated. Or maybe I just committed a type 2 error. I just happened to get two samples that were sort of far closer to each other than I would expect based on the actual distribution here. It's tough, I don't know from based on one study what's going on. That's sort of up to me to go through and try and piece apart and sort of think critically about where I'm at and what I've got. This is where meta-analyses start to become very important, because I can go through and say where people tend to fall on this stuff. All right. Think about power analyses versus our confidence intervals. Another thing that people will try and do is we'll go through and calculate a confidence interval. And remember that values that are falling outside of our interval estimate, these are non-refuted values, right? Or excuse me, values within my interval are non-refuted values. These are plausible estimates. These are things, well, this is my point estimate, but my confidence interval says anything in this range could be a reasonable guess for what the actual population parameter is, right? And if we have our values clustering tightly around the null hypotheses, then we can start to say maybe there really is no effect in these data, right? So if I've got a lot of people in my sample, right, what does that do to the width of my confidence interval? Brings it down, right? And if I've got a lot of people in my sample, and I've got a really tight confidence interval, and my confidence interval circles very tightly around that null value, around 0, my confidence interval ranges from like -0.2 to +0.1. I've got a lot of people, that's pretty good. That's better evidence suggesting that maybe actually what I have here is a null effect, or if there's an effect there, it's too small to make a bit be of any difference, right? But if I'm in a situation, Evelina, where I've got a null effect, but my confidence interval is quite large around 0, right? Or just barely eclipse 0, this might be a situation where I might be more cautious about saying, yeah, nothing to see here. There's really is, the null is true, right? We never say we accept the null hypotheses, but if we got in a situation where we had a large sample, very precise interval estimate, and 0 falls dead center in the middle of that 0 estimate, we might say, yeah, I mean, we're not saying that there's nothing there, but based on this interval estimate, it really suggests that there's not much there to be had. Okay? But with observed power and things along these lines, people will then start to go through and say, okay, well, I say parameter estimate, lower bound is this and the upper bound is this, based on the data that I've collected. These are reasonable values for the true population parameter, right? And Haley, you do this. You said, looks like, based on the data that we've collected, reasonable values for the population parameter somewhere between 15 and 30, or 15 and 23. So that's our interval estimate. I'm like, okay. But what if it's 28, right? what if it's actually 28, and then I want to go through and power my analyses to sort of assume that it's 28. Well, it's a free country, you do whatever you want, right? But based on the data that I've collected, 28 is not a reasonable value, right? I can power something to population or parameters with that characteristic, but that doesn't make any sense. I'm way outside the bounds of what seems to be reasonable for this anyway, right? And so if we go through and we calculate our confidence intervals, we can start to use this to say, okay, what are reasonable estimates for this population parameter, right? And this can be useful when we're calculating confidence intervals around effect size. We could say, all right, I've only got one measure of effect. There's only one study that's done what I wanted to do, and I've gone through and calculated an effect size. But then what I might do is I might calculate a confidence interval around that effect size to say, all right, what's based on these data, what's the lower bound for that confidence, what's the lower bound estimate for that effect size based on the data that these people have provided, right? And what I might want to do is then go through and power my next study at the low end, right? And maybe I'm not excited about the number of people that it's suggesting on the low end of that effect size, but what we'll see in a moment is the confidence intervals around effect sizes are quite large, right? And if I've only got one estimate to work with, and I don't have the benefit of power analyses, right? What I might do is I might say, all right, well, here's the effect size that they're reporting. I'm going to calculate an interval estimate around that, and then say, all right, well, here would be the number of people I would need if we're assuming that this is sort of a good estimate of the population parameter. But I know that this is going to vary. It could be as low as this. How many people would I need in order to adequately power the study for the low-end estimate based on this data, right? So again, talking about looking at our interval estimates as values that are supported by the data, and then not trying to use values that fall outside of that to say, oh, well, this is what I'm going to do, or this is what it's a big what if. I don't know, what if I could fly around the room? That'd be cool, but I can't. So it doesn't make much sense to sort of think about that as a possibility for any such thing, right? You kind of see what we're working with here? All right.
So confidence intervals around your effect size would be a way to kind of take your research a step further and see what what are we really looking at as far as population general,
Right.
being able to generalize onto the bigger population?
Exactly, right? So we've been talking about Haley's study that had an estimate of effect that was way large, right? But if Haley then calculates confidence interval around her effect size, we might see you got an effect size of 0.8, but we see the lower bound for that is actually 0.2. It's often what happens with these, right? Particularly if you didn't have a lot of people in your sample, right? And so I go through, and instead of, and if you've done that for me, or if you've done that legwork for me, then I might say, well, this is what she found, but based on the data that's pretty imprecise, it could be as low as 0.2. So what I'm going to do is I'm going to take the high road and power my study to find a D of 0.2. And I'll probably like, best case scenario, I save myself time and effort from sort of spending a lot of time in research that wasn't going to ever find an effect anyway, not because it's not there, I just was underpowered. And then two, even if Haley's does have a good measure of effect, it actually is about 0.8, then I'm hugely overpowered and I'm guaranteed to find my effect, right? And so this is what we start, and then so Nick runs his study, and John runs his study, and Emilio runs his study, right? And they find they're getting effects in the 0.3 range, right? But if you said, hey, this is my effect, this is the interval around my effect, then these guys are saying, like, well, it looks like sort of our data aren't inconsistent with what she's found, right? Now, the more people start to find effects around these guys' size than around your size, yours is starting to look like the outlier relative to theirs. But we can start to use this to say, because just on the face of it, if your effect is 0.8 and mine is 0.2, I'm saying there's something weirdly different here, but when maybe there's not, right? Your effect just had a big interval around it, which is typically what we find, okay? Which gets us into the issue of confidence intervals around effect size. To this point, we've been calculating confidence intervals around point estimates of means and different statistics parameters, things along these lines. That's a nice, even, symmetrical distribution, right? We find our standard margin of error, and then we plus or minus that. Now the problem is that sort of, or what makes this nice is that we're confidence intervals for means and sort of many of our other statistics are based around this central t distribution. Central t distribution centered at 0, and the shape of this distribution determined by our degrees of freedom. Remember, our t distribution is a family of distributions, and if I know what the degrees of freedom are, that tells me the exact shape and probabilities associated with that t curve, right? And we use this because our null hypothesis tests are assuming a mean equal to 0. Our value, no value under the null hypothesis is 0, right? And if that's true, then I'm going through and I'm calculating my t statistic based on the right population value, and sometimes I'm going to get a t statistic that's less, sometimes I'm going to get a t statistic that's a little more, but we're going to be centered on 0, right? Problem is confidence intervals for effect size aren't assuming 0, right? If it was assuming 0, we wouldn't need to worry about effect size to begin with because the effect is 0 because there's nothing going on, right? And so what we need to do then is start to get parameter estimates around this non-central t distribution, and this starts to become more difficult. Non-central t is not symmetrical, and it's not centered around 0, right? A non-central t is centered around our non-centrality parameter, gives us the center point of that distribution, and so we need to know both the degrees of freedom and the non-centrality parameter to start getting sort of interval values for that. So the t distribution that we know and love, that we're using in GraphPad and in our tables and things like that, that's our nice central t distribution. Our non-central t distribution has properties that are mysterious and that we don't know and that aren't booked anywhere because they're based on not only the degrees of freedom, but how far of an effect we've got, how big of an effect, how far of the shift is that we're looking, okay? So our non-centrality parameter is going to give us the point that's going to be the center of that non-central t distribution. And this non-centrality parameter, again, is kind of like a measure of effect. Just like sum of squares is a measure of variability, not an interpretable measure of variability, right? If I say, Emilio, I got a sum of squares of 5 billion, is that a lot of variability or not a lot of variability? I don't know, right? It's not meaningful in terms of interpreting things. Non-centrality parameter, the same type of thing if you think about this in terms of effect size. Your non-centrality parameter tells you how much of a difference there is between the null and your actual population looking at. It's a measure of effect size. It's just not a measure of effect size that has any sort of standardized interpretive value like a Cohen's d or something along these lines. Okay, so again, sort of our non-centrality parameter telling us the difference between where our non-central t is centered versus where our null is centered. Okay, and so calculating confidence intervals around effect size now involves finding out what that non-centrality parameter is. Okay, but because our effect sizes are a linear function of our non-centrality parameter, what we can do is we can find what that non-centrality parameter is. And then we can use that and that distribution to determine where our sort of plus and minus points are for that. And then once we have confidence intervals around a non-centrality parameter, we can work backwards then to go through and calculate confidence intervals around our effect size. Okay? So the first thing we need to do if we want to calculate confidence intervals around our effect size, we need to find our non-centrality parameter and calculate confidence intervals around that. So if we're thinking about our non-central t distribution, what makes this tricky and why this has been hard for so long is we haven't had the computational power to do this reliably. Even when I first started out trying to do this, it was me screwing around in R with sort of pointing values and trying to get approximations into something close that was to what the non-centrality parameter we were looking at for a given design. What we see is this non-central t distribution, right? If this is t distribution, a central t distribution with 60 degrees of freedom, 20 degrees of freedom, 5 degrees of freedom, right? What we see is that as we start to increase our non-centrality parameter, one way or the left, right? As our effect sizes get larger and larger, right? What we see is that we start to get more and more skew in our non-central t.